Hello, my dear friends. In this lecture, we are going to be looking at a discussion about Fourier series. And then our discussion is going to be based on what a Fourier series is, general expression of the Fourier series. We'll look at the applications of a Fourier series and the half-range Fourier series. So keep tuned in and remember to subscribe, comment, and like. So my dear friends, a Fourier series is a way to represent a periodic function as a sum of sines and cosines. Essentially, this allows you to express complex periodic signals in terms of simple harmonic functions. So if you have a function such as y is equal to x, and which is defined over a period, -1 less x less 1. Now, what we can do, we can express this on a Cartesian graph. So this represents a graph of y is equal to mx plus c. So the y-intercept is 0, so meaning it is going to be passing through the origin. So let us assume we have -1 here and we have 1 here. So this is going to be moving through the origin like that. So the period for this actually now becomes t is equal to 1 minus 1, and this is equal to 2. So meaning the period is 2. It is, if it is a periodic function, it's a very important component. You must have a periodic function for you to express it in terms of cosines and sines. That is, as a Fourier series, it must be periodic. So if the period for this is 2, meaning that after 2 units, it is going to be repeating this pattern. So we shall jump 2 units, and this becomes 3. So 3, and this line is going to be, the line passing through here is going to be parallel to this. So this is how it's going to be looking like. Then again, if we do the same with the other side, 2 units here, we go to -3. So if we draw here also, this is going to be something like this. So now, we already have, this is y, this is x. So what does this mean? We are now going to express it as a Fourier series. So when you express it as a Fourier series, this is what you're going to have. So we have -1, we have 1 here, we have 3 here, we have -3. So this is what is going to happen. You're going to have something like this. So now this is going to be in terms of sines and cosines. So then you have something like this, then something like that, then you go down. So that's how this finally is going to look like. So this one is now a plot of the Fourier series. This is f of x, and this is x. Where is this very applicable? We shall look at it at its applications in engineering, in math, in physics, studying the quantum mechanics, looking at solution of partial differential equations, here looking at digital signal processing. That is in the electrical and electronics engineering. So who is the guy behind this Fourier series? It was named after Jean-Baptiste Joseph Fourier, who lived the 1768 to 1830. This guy showed that any periodic function can be decomposed into a sum of sines and cosines, provided that the function satisfies certain conditions. And these conditions, they are the ones that we shall later on in the future know that they are Dirichlet conditions. Obviously, the Dirichlet conditions, first of all, determine or define the convergence of a Fourier series, but also those conditions are important for there to exist a Fourier series within a function. And we shall see that the function must be periodic, it must have bounded variation, it must be integrable within the given period or given range. So those conditions are very important for there to exist a Fourier series. So let's look at the mathematical definition of Fourier series. If we have f of x, okay, being a periodic function, so that there exists a small value t for which f of x is equal to f of x plus that t, which is now going to be called the period of the function. This is the same as f of x plus 2t. This is equal to f of x plus nt, whereby n is an integer. So that means this f of x, if this now is confirmed that it's a periodic function, then it can be expressed in the form of a Fourier series, whereby it is now going to equal to a naught plus sum from n is equal to 1 up to infinity. Then we are going to be having a sub n cosine n by x out of r, whereby r is half the period. In other words, this function is going to be defined over an interval negative r to r. So then we add another one, sum from n is equal to 1 up to infinity of b sub n sine n pi x out of r. So we will later on see that a naught is now the average component or the DC component of the function over the period. So over one period, we shall be calculating a naught. So in other words, for example, here, if you talk about one period, the value of this function is going to be a naught. Then it will also have now, when you go ahead, you will be having either something like a1, cosine something, then b1, depending on the nature of this function. Then whatever has a1 or whatever is having n is equal to 1, this is what we actually call the fundamental component. The fundamental component of the harmonics. So of that Fourier series. So meaning in the future, if they ask you what is the fundamental component, you just take that component that has n is equal to 1. The DC component or the average value of this function over one period is a naught. So you need to understand that. And we are saying that it is a DC component because it captures the average value or zero frequency component of the function over one period. It's a constant term in the Fourier expansion that accounts for the overall offset or baseline level of the signal. Then we have also talked about A sub n and B sub n. These are Fourier coefficients that determine the amplitudes of the sine and cosine terms. The sum is over all integer values of n, which correspond to the harmonics of the signal. So let's see how these coefficients are determined. So if we have the function defined over the interval negative r to r, then a naught is going to be 1 out of 2r integrating from negative r to r f of x dx. Then an is going to be 1 out of r integrating from negative r to r f of x, then cos n pi x out of r with respect to x. Let's look at sub n. B sub n. B sub n is equal to 1 out of r negative r to r f of x sine n pi x out of r with respect to x. That's how we can calculate B sub n, which is called the sine coefficient. So this is the sine Fourier coefficient, and this is this A sub n is actually called the cosine coefficient. So once you know how to calculate this, then you'll be able to express any function as a sum of sines and cosines. But before we do that, let's talk about something in details. Some important properties here that we need to discuss. Now, if you have an odd function, you multiply by an odd function, you get an even function. How is it possible? Let's look at e.g. if you have x power 3 plus, okay, times x power maybe 5. This is an odd function, this is an odd function. This is going to equal to x power 8. So you can see that if you have an odd function times an odd function, you get an even function. This property is going to help us in calculating these coefficients. Let's look at another one. When we have an odd function times an even function, this is going to give us an odd function. Take an example. If we have x to power 3, that is an odd function, times an even function like x squared. This is x to power 5. This is odd. This is even. Let's also look at another case where you have an even function being multiplied by an even function. This also gives you an even function. Take an example. If we have x squared times x to power 4, this gives you x to power 6, and this is an even function. How does this help us? Take an example. If we are integrating an odd function like x, maybe to power 3, sine n pi x out of r with respect to x from negative r to r. This one already is an odd function. This is an odd function because the sine function is an odd function. And this is going to give you integrating an even what? An even function from negative r to r, then even function with respect to x. This one, as long as this is not a piecewise function, then it is going to give you 2 or twice integrating from 0 to r of x cubed sine n pi x out of r. Okay, but even if it is even if it is a piecewise function, but as long as it is giving you this kind of a scenario, then it should give you something of this sort. Now, take an example. Maybe this is a little bit complicated. Let us take an example of if we were integrating an even function like cos x from negative r to r with respect to x. This one itself is going to be sine x, okay? This is going to be sine x from negative what? From negative r to where? To r. This becomes sine r minus sine of negative r. This is giving us sine r plus sine r, which is to sine r. So does it imply that integrating negative r, integrating from negative r to r, cosine x with respect to x, that this is equal to twice of integrating from 0 to r cosine of x? Yes, with respect to x, this gives you sine, okay, x from 0 to r times 2. This is 2 sine r. So this is very true. Now, look at another case. If we were integrating an odd function, let us assume we had x maybe cubed times cos n pi x out of r with respect to x. Maybe we are calculating for a sub n. This is what we interface. So you'll find that we are integrating an odd function from negative r to r with respect to x. What does this give us? E.g., say the odd function is equal to sine x. So assume that you're integrating from negative r to r sine what? Sine x with respect to x. This one is going to give you 0. How? You see, I'm going to have this becoming negative cos x. From negative r to r, this gives us cosine R, okay, put a negative outside, then we say minus cosine of negative R. We know negative cosine of negative is always a cosine of a positive. So cos R minus cos R, this gives you 0. So once you understand that I'm integrating an odd function, for example, over this defined interval, negative R to R, usually this changes when you're dealing with some piecewise functions. Some piecewise functions, you find that it will be a little bit different, whereby you need to put the whole function. For example, you can have f of x equivalent to, let us say that this is 1 from negative 1 less x less 1. Then you have this equivalent to negative 1. Then you're integrating, okay, you have this one equivalent to negative 1 from 1 less x less 3. So you can see that this is a little bit different, and you need to carry out all these integrals. That means you have to integrate f of x, sine something, then from negative 1 to 1 plus negative 1 times sine from 1 to 3. So this one may not be the same as this. But if you have those direct functions where they have just defined the function and is not piecewise, and they have given you the period, then just know you having the knowledge of this is very important, because like here, you'll not waste time doing the integration. You'll just say this is equal to 0 and you move. Let's take another example. You could be integrating, maybe you have a function like x squared times cosine n pi x out of r with respect to x, negative r to r. So this one, you see, it is equivalent to integrating from negative r to r of a what? Of an even function with respect to x. So this one is not equal to 0, so you have to go through the rigorous methods of integration, like integration by parts, because you have a function and then like a polynomial function and a trigonometric function. So when you have such as a product of each other and you're integrating, then you can be helped by integration by parts. So that is a simple way how you can do easily these coefficients. So having this knowledge is really very powerful. Now let's look at the applications of a Fourier series. So signal processing is one area whereby we have audio signal analysis, decomposing periodic audio signals, for example, music and speech, into frequency components. So here, the mathematical tool that we use is the Fourier series. Filters design. So when you're designing filters for periodic signals, like low pass, high pass, and band pass filters, we use a Fourier series as the mathematical tool. Then in electrical engineering, in circuit analysis, for example, in AC circuit analysis, we need to analyze periodic voltages and currents, their waveforms. So in analyzing these waveforms, we'll find that a Fourier series is very important. Then power systems, such as in power electronics, we use it to study harmonics in power systems, and this helps us to design the appropriate harmonic filters, because we are able to look at the response of such a system with respect to a given frequency. Then in mechanical engineering, we look at vibration analysis in the design of, for example, shock absorbers. We needed to look at to what extent does the vibrations that come into the machine as a result of maybe a pothole, so that come into the vehicle, we need to take them away as soon as possible so that we maintain the comfortability of the occupants. So analyzing those vibrations to what extent or what is bearable, what is not bearable, we use the powerful mathematical tool, the Fourier series and Fourier transforms. Acoustics, studying sound waves and designing acoustic systems, such as in the design of speakers and microphones, and analyzing those acoustics. Then we are using the mathematics behind it, and that is the Fourier series. Then the waveform, wave phenomena, we are looking at analyzing periodic wave propagation, interference, and diffraction. So in physics, wave phenomena, we look at the application of the Fourier series in analyzing periodic wave propagation, interference, and diffraction. Here we are discussing about the light waves and sound waves. In mathematics, we use it to solve partial differential equations. An example is the heat conduction equation and the wave propagation equation. Then function approximation. We said that we can compress or express a function as a sum of sines and cosines. So that is basically function approximation. Because if you have f of x equivalent to x, then you can say f of x is approximately equal to a naught plus sum from n is equal to 1 up to infinity of an cosine n pi x out of L. That is if you talk about half-range Fourier series. Then the music and sound synthesis, we talk about this usually in music theory, analyzing the notes and chords, that is decomposing these into harmonics. Then we will find that the powerful tool is going to be the mathematics, and that is the Fourier series. Sound synthesis, generating complex sounds using sine waves of different frequencies. We just express this, we design a sound, and then we be able to generate different sounds by maybe changing the frequencies. And all of that is possible because we are able to express a function as a Fourier series, and then later on you do a Fourier transform. Fourier transform, we are talking about changing from the time domain to frequency domain. That is what we mean by Fourier transform. So in image processing, we look at JPEG compression using discrete cosine transform. That is a variant of Fourier series for image compression. You could be changing also, even by the way, even in video and audio processing. So where you compress a video from one form to the other. For example, changing from MP4 to maybe 3GP, so that you are able to have this video visible on some small analog phones. So you'll be able to view this video and actually enjoy. But if it was maybe in MP4, we would not be able to do that. So the math that helps us to change from MP4, compressing an MP4 file to a 3GP file, is a Fourier series, and of course with the help of a transform. In control systems, analyzing the frequency response of periodic systems, we apply Fourier series and Fourier transform. Now let's talk about half-range Fourier series. So you could be given a function and you're told to express it as maybe a cosine series or sine series. So here obviously we're talking about half-range cosine series, cosine Fourier series. And this is, if you have f of x, this is going to be a naught plus sum from n is equal to 1 up to infinity of an cosine n pi x out of L. That's the only component that you'll be dealing with. So that means even if you're given an odd function, even if you're given an even function, you just have to extend it evenly. So this, you have to extend the function evenly. You could have been given a range from 0 less x less pi. So what you're going to do, you're going to be now using a range of negative pi less x less pi, but then you'll now consider the even part of this function. Now for a sine series, here you extend the function oddly. So meaning here you're going to be using the the techniques that help you to actually make it an odd function. So here you have f of x equivalent to a naught plus b, okay, sum from n is equal to 1 up to infinity, b sub n of sine n pi x out of a. So this becomes half range sine Fourier series. And this is half range cosine Fourier series.